The next chapter we're going to look at is called projectile motion. We'll look at both free fall and objects moving as projectiles in this chapter. In this chapter we'll have kinematics not just in one dimension but in two, so that'll add a little complication to the things that we've already been working on. Basically, it's a lot of who cares equations, so if you get good at those, that'll take you a long way in this chapter. So a couple quick definitions. What's a projectile? Anything traveling under the influence of nothing but gravity is a projectile. So if you throw something, it's a projectile. As long as something's moving through the air and doesn't have, say, a rocket pack attached to it, that's technically considered a projectile. The path the projectile takes is called trajectory. Again, just quick vocabulary words, not much else to say about that. The first section we're going to look at is strictly free fall. So we're not going to add that horizontal component in yet. We're going to start with things just moving strictly up and down. So a few things that we should know for this. If you have anything that is a projectile, its vertical acceleration is always 9.8 meters per second squared as long as you're on Earth. Sometimes you'll get some goofy problems that will ask you about objects on different planets, but as long as you're on Earth, you're going to use 9.8. You will oftentimes see the symbol G for the acceleration due to gravity. So whenever you see that, that's just the constant 9.8 meters per second squared. Usually if you're talking about a free fall problem, they don't list that in the problem. You're supposed to know that. So you'll oftentimes see problems in this chapter that don't give you very many numbers in the actual problem, and you have to pull things like gravity out of your own knowledge to add as a variable for the problem. Here's an interesting thing we can do with signs. In this chapter, most of the time things are moving down. As a result, you would get a whole bunch of negative signs. Usually we say up is positive, down is negative. But if you have a problem with a whole bunch of negative signs, one thing that you're allowed to do in physics is say that down is going to be positive. So if you do that, you're basically taking all those negative signs and making them positive, and that completely works in a problem. The thing that you have to be careful of is that the signs have to all agree. So if things are in the same direction, should have the same sign. If things are in opposite directions, they should have opposite signs. If that completely messes with your head, you can just do the traditional down is negative, up is positive, and that's just fine. But you'll see my examples, oftentimes when I'm able to, I make down positive so I don't have so many negative signs in my work. So here's the first example. So we drop somebody off a cliff. So the question is, how far does he fall in each successive second? Here, everything is down in the problem, so this is an example of a case where it's best to make down positive. So in this case, I've got my initial velocity is 0 because they said it was dropped. You'll have to make that assumption a lot of times. If they don't tell you the initial velocity is something, you can usually assume that it's 0. So my acceleration due to gravity is 9.8. Here I made it positive. I often put little arrows at the end to remind myself that, okay, that's down. And then I can check my variables and make sure the things that are down have the same sign. So my unknown, in this case, I'm looking for distance, and I don't care about how fast he's moving. So I'm going to use the who cares then for final velocity. Again, that should be a sub v, v sub t. It just loses my subscripts when I import this PowerPoint in. So there's my who cares equation that I'm going to use. And notice, because you're adding two things together, this is where it's really going to mess you up if you mess up the signs. So if they should both be positive, or if one should be positive, one should be negative, that's really important in any equation where you have addition going on, because that'll give you not just the wrong sign on your answer, but actually the wrong numerical value. So that's pretty important. You might see, by the way, this equation with 1/2 gt squared. I normally just use a, but g is technically not just any acceleration, but specifically the acceleration due to gravity. So you could use that in any of these free fall problems, and that would be fine. You might see it either way. So here I go ahead and put my numbers in, do the math, and I get a distance of 4.9. Here's a nice thing to think about. Especially if you're doing multiple choice problems, sometimes if you can get a quick estimate, it's actually better than sitting through and working out all of the numbers. And that just saves you time if it were any type of a test where you're timed. So here's something quick that you can do is 9.8 is awfully close to 10, so let's say I call that 1/2 times 10. Since 1/2 times 10 equals 5, I could in general just say that 5 times t squared is going to give me my displacement, assuming no initial velocity. So here's a real quick way to do it. So look, in this case, 1 squared is 1 times 5 gives you a distance of 5 meters. So after 1 second, you've gone pretty close to 5 meters. So that's a real quick way to do an estimate or to check your answers, that sort of a thing. So after 2 seconds, if t is then 2, 2 squared is 4 times 5 is 20. So you get about 20 meters after 2 seconds. For 3 seconds, 3 squared is 9. 9 times 5 is 45. So you're going to get approximately 45 meters. So that's how you can do that really quickly. Here's my answers worked out to using 9.8, but you can see they're really close to my estimate. So that can be a handy way to approximate quickly. In general, you can say as a relationship that displacement is proportional to the square of time. So if you were to do some kind of a graph with x and t, it would be a top opening parabola. Okay, so here's my part B. So how fast will it be traveling? So in this case, I've switched, and my unknown is now v, and my who cares is x. I could use the x's that I just solved for, but in general, that's never a good idea in case you made a mistake with the x's. So we're going to use who cares for x, and we're going to solve for v. So this is just more using the who cares equations. Again, I simplified this. If you have no initial velocity and you're going to use 9.8 for acceleration, you could use that equation as well. It's the exact same thing. So I just put my numbers in, and I can say 9.8 meters per second squared times 1 second is 9.8 meters per second. Here's another place where you can do a little shortcut. Again, if you round the 9.8 meters per second squared to 10, you could take that 10, put my unit on there, times the time, and that'll give me a real quick estimate of how fast something is going. So for 2 seconds or 3 seconds, I think you can just see that you would just take that number times 10 and you have a nice direct relationship there. So after 2 seconds, you're going about 20, which is what this number says, 19.6 is just about 20, and then just about 30 for 3 seconds. So velocity is directly proportional to time. If you were to graph that then, v and t, you would have a linear relationship like that. So it does get just a little bit more complicated when you have an initial velocity, especially if the initial velocity is the opposite direction of gravity, because that's when you really have to pay attention to signs. So in this case, we have an initial velocity upwards, and we're going to see how high that it goes. Now in this case, since I have both directions up and down, I'm not going to mess with the signs at all. I'm going to let up be positive and down be negative, and I do have to keep track of that as I go. So here's my knowns. I know the initial velocity is 20 meters per second up. I know my acceleration due to gravity is 9.8 meters per second squared down. So I know they've got to have opposite signs. Now here's something that you can make this assumption that at the very top of that throw, that initial velocity, or that final velocity, when it reaches the very top, is going to be 0. In general, here's a quick problem-solving tip. It's kind of a side note from this problem. But let's say we have something that's thrown upwards and goes down. If its velocity at the beginning here is 20 meters per second, the velocity when it reaches the same height on the way down is also going to be 20 meters per second, just in the opposite direction. So I could make that negative. That's supposed to be a negative there. Okay, the velocity at the very top of that peak, that's going to be 0. That's right at the instant it's changing directions from going up to going down. It has a very small instantaneous moment where its velocity is 0. Anywhere along this, acceleration is 9.8, even at the top. I sometimes have students say acceleration at the top of a throw like this would be 0, but it's not, because gravity is still working, so the acceleration is still 9.8. And acceleration then down here at the bottom would also be 9.8. And in this case, we'll say it's negative since we have 2 directions going on. One last thing that can be useful in problem solving for projectiles is to know that the time it takes to go to the top is the exact same as the time it takes to go to the bottom. So time up equals time down. Okay, that can be really useful to know. So if you have a problem where you've solved for the time it takes to go to a certain height and they ask you the total time it's in the air, in that case you could just double it, and we'll see some problems like that. But that's kind of all the handy problem solving stuff that you're going to see. So now let's go ahead and return to this particular problem. So we've got our knowns and our unknowns. And so now we can go ahead and just do the who cares math. So we've got our who cares for time to begin with, and we use that and we solve for x. And notice here that I have my initial velocity is positive, my acceleration is negative. Because these two terms are added together, if you mess up the signs, if you leave your acceleration positive and your velocity positive, that would give you the wrong answer. So you do have to be careful about which direction things are going. So part B, how long does it take to return to its original height? There's more than one way that you can solve this. You could solve for how long it takes to go all the way to the top. You could solve for the time up and double it, like I was just saying a second ago, and then take it times 2. Or the way that I work this particular one out is I said your change in position is 0 because you end at the same height that you started with. So that's something else that you can use. So I'm going to do it this way. Find my initial velocity, my acceleration, and my x. My v I put as who cares, although you could use a negative 20 meters per second as the final velocity, and that would be correct as well. So more than one way to do these. So I went ahead and did who cares for v and solve for time. So when you do that, you end up with a quadratic. Anytime that you have an initial velocity in these problems, you're going to end up with a quadratic. So that's why I gave you guys that quadratic solver program for your calculator. If you missed that, or if you somehow get it messed up on your calculator, just ask me and I'll give that to you so you can use that. So I end up with my quadratic. One of the roots is negative, so I stick with a positive one since we're talking about time. And that's it for this one. On the next one, we'll add just a few more details about Freefall in it.